raising and lowering indices. That kind of I kind of seem to forgot about that, so I'm going to just put that back in right here before we move on to the Christoffel symbols and try to develop a derivative idea for tensors. That is still a tensor. So let's look at the metric tensor one more time, just kind of like remind ourselves what's going on with the metric tensor. It seems like I got a little bit of a problem here in my display. Let me see what's going on. Seems kind of far off the screen. Okay. All right, so let's look at the metric tensor just a little bit more today, and then we'll move on to something else that is going to help us start to look at some way of like defining some sort of derivative of a tensor that is still a tensor. So the metric Gij we defined as z sub I dotted with z sub j, where z sub I was the partial derivative of the position vector with respect to the xi coordinate. Right, r in Cartesian representation was xi plus yj plus zk. Right, so that's what it would be in Cartesian coordinates, and we talked about this quite a bit. So then this metric tensor is the dot product of those covariant basis vectors. So these are the covariant basis vectors, and we talked about that already as well in depth. This is the covariant basis vectors. All right, and also what else have we talked about? We've talked about inner products. So inner products. We talked about maybe like SIR, TRK would produce a 1-1 tensor. Right, and we could call that something like PIK equals SIR TRK. So that would basically produce a matrix. Right, they would produce a matrix. So what we can do, so now we can consider some tensor of rank 1, we'll call it Ti up, multiplied by Gij down. So this is, or will produce, a covector. Of course, that's just a shortened way to talk about a covariant tensor of rank 1, a covariant vector field. And we could call that thing, we could call it Pj down equals Ti up, Gij down. So that would produce a 0-1 tensor, Pj down. But what if we look at Ti up, Gij in more depth, like more in depth? That's going to be Ti up, Zi down, dotted with Zj down. Right, we just implore the definition. We explicitly put in the definition of the metric in terms of the covariant basis. Zi down, dotted with Zj down. Now I can say that's actually Ti up, Zi down, dotted with Zj down. Okay, and now that is the vector T, the vector field T, dotted with Zj. One can then show that this is actually the components of the vector T, and it's actually the covariant components of the vector T. So this dot product is the covariant components of T. So when you dot T with its jth covariant basis vector, you get the jth covariant component of T. And you could, I'm not going to go through a more in-depth derivation, but this is actually Tj down. So we'll call it Tj down. So Ti up, Gij down is actually Tj down. So we can actually find the covariant component of T. So covariant components of the vector field T. Whereas we started with the contravariant components of the vector field T. So to basically lower the index, we just multiplied by the covariant metric tensor. So that would lower our contravariant index. Okay, does that make sense? Again, I'll pause for questions, make sure everything's clear before we move on. Okay, well, for example, lower the two indices of, we'll call it R, I, J. So the way we could lower these indices is we could say, okay, Rij multiplied by Gim. And so that would lower the first index. We call it Rjm. So we lowered the I. So this lowers the I index. And then we can take that, Rjm, and multiply it by Gjn, and we get something called Rmn. And that lowers the J index. So then we need to take Rij up, multiply by Gim down, Gjn down, and that leaves us with Rmn down. So this would lower both indices simultaneously. So it's the same, it's not exact, it's the same tensor, it's just got different indices now. So the components will be different, but it's still got like the same type of information in it. It's just now the covariant information versus the contravariant information. The thing it represents is still, the same. It's just now represented using covariant indices. So you can raise and lower any index of any tensor anywhere by multiplying by a metric tensor. So you can also raise the indices. So raising indices just requires Gij up, which of course we knew was Gij down inverse. So this was the contravariant metric tensor. And so when you multiply by the contravariant metric tensor, you raise an index. So contravariant metric tensor. For example, say you have R LMNS, and you multiply RLMNS by GLK, and you get RKMNS. So now you've got one index up and the other three down. So you basically raised the first covariant index on that tensor by multiplying by the contravariant metric tensor. So this raised the first covariant index. So that's more or less how we raise and lower indices. We just multiply by the covariant metric tensor if we want to lower an index, or we multiply by the contravariant metric tensor if we want to raise an index. Again, the contravariant metric tensor is just the matrix inverse of the original metric tensor that we defined. Cool. Questions? And then the last thing really I should mention is the generalized inner product. So generalized inner product is really if you have two vectors u and v, then Gij ui up, vi or vj up is the generalized inner product. So that's the last thing I really want to mention from chapter 5. Again, we already kind of went over both of these concepts in the worksheet accidentally before I introduced them, so that was my bad. But let's move on to chapter 6. Unless there are any questions, I'll pause for questions. See if anybody's got any questions. Okay, cool. Let's look at chapter 6. It's called the covariant derivative, or the derivative of a tensor. So chapter 6. The derivative of a tensor. And by derivative, we mean the covariant derivative, because we will introduce a covariant index once we take the derivative. All right, so recall we have zi down is equal to partial r partial xi, like this. It was the rate of change, or how the position vector changed with respect to the ith coordinate. That was the ith covariant basis vector. So this is the covariant basis when I consider all I values. Recall, these vectors may change orientation and length depending on location. Right, and we looked at this with E sub r and E sub theta. E sub r points away radially from the origin. So that's Z sub r. And Z sub theta goes around the circle like this. And it actually gets longer if you don't normalize it. So our basis vectors might change their orientation and their length throughout the space. So what we want to do is capture how the basis vectors, the covariant basis, changes throughout the space. So we will capture how the covariant basis changes throughout the space, or with respect to each coordinate, with respect to each independent variable. So that's what we're going to do right now, because this is going to play into the fact that if we're trying to take a derivative, that's really just rates of change, right? Well, if our basis vectors are changing, we kind of have to take that into account. So that's what we're doing first, is we're looking at what happens to our basis vectors when we move about the space. We're trying to capture their rates of change right now somehow. Okay, so we're going to do this with what we call the Christoffel symbols. So Christoffel symbols. So the Christoffel symbols are going to be the components of the rates of change of the vectors expanded about the covariant basis. Okay, so consider partial zi partial xj. Partial zi partial xj is a vector, right? It's a basis vector differentiated with respect to some independent variable. So it is a new vector. So the change of the ith basis vector with respect to the jth coordinate. How does this basis vector zi change when I change xj a little bit? So this is a new vector because zi is already a vector. We can expand any vector in terms of the covariant basis. So we'll call this partial zi down, partial xj, something times the covariant basis, we'll call it zk down. So what are the components of this vector when I expand it out in terms of the covariant basis? So that's the notion that we're trying to get across here. And we call these things the Christoffel symbols. So gamma ij down, k up. And these are the components of partial zi, partial xj with respect to the covariant basis. So if I were to take this vector partial zi, partial xj, and expand it out in terms of the covariant basis, it would have components, and I'm calling those components gamma ij down, k up. So more in layman's terms, gamma ij down, k up is the kth component of the derivative of the ith covariant basis vector with respect to the jth coordinate. Cool. So that's what this thing we call a Christoffel symbol. We're actually going to call it the Christoffel symbol of the second kind. So we call this a Christoffel symbol of the second kind. You might say, well, where's the first kind? Well, the first kind is basically where they're all down, I think. Basically, I, J, K are all covariant. Well, this thing's not technically a tensor. It's tensor if you have orthogonal coordinates or orthogonal coordinates, but if you have curvilinear coordinates, this thing is not a tensor in general. So, so we call this thing Christoffel symbol of the second kind. And it's really just the components of this derivative vector with respect to the covariant basis. So let's compute the Christoffel symbols in 2D flat space for polar coordinates. So example, compute Christoffel symbols and 2D flat space for polar coordinates. So the solution here, we have our position vector is xi plus yj, which is equal to r cosine theta I plus r sine theta j. So z sub r is equal to cosine theta I plus sine theta j. And z sub theta is equal to negative r sine theta I hat plus r cosine theta j hat. So those are our two basis vectors. And now we want to, well, how do you get those? Don't forget, right, this is just partial r, partial little r, and this is partial capital R, partial theta. So that's how we got those. Now, consider partial ZR, partial R. Well, that's going to be 0I plus 0J, right? Because there's no R anymore, which is actually 0Z sub R plus 0Z sub theta. And let's just make a note here that we're saying x1 is R and x2 is theta. So this tells me that this first component, which would be gamma 1, 1 down, because I'm differentiating z1 with respect to x1, and it's the first component. So gamma 1, 1, 1 is 0. And same thing for gamma 1, 1, 2 is also 0. So my first two Christoffel symbols are 0. Don't forget the two indices down are the vector you're differentiating with respect to which coordinate. Okay, so here we're differentiating z sub r with respect to r. Well, that's x1, or z sub 1 differentiated with respect to x1, so we have two ones down. The first component is coming from the fact that this is really just z1 here, and this is z2. So z1 plus 0 z2. So I have my first two Christoffel symbols. Okay, well now take z sub r and differentiate it with the theta. So differentiate zr with respect to theta. We get negative sine theta I plus cosine theta j, which looks an awful lot like 1 over r times z sub theta, which we could write as 0 zr plus 1 over r z theta. That gets our next two Christoffel symbols. So this would be gamma 1, 2, 1. So 1 up and 1, 2 down. And that's 0. And then this would be gamma 1, 2 down, 2 up is 1 over r. It's just the derivative of z1 with respect to x2. And then the first component, which is the 1 up on the gamma, is 0, and the second component, which is 2 up on the gamma, is 1 over r. Okay, we'll now differentiate z theta with respect to r. So partial z theta partial r is going to be cosine theta I plus sine theta j, which is going to be 1 over r z sub r, which is 1 over r zr plus 0 z theta. And we get our next two Christoffel symbols. Gamma 2, 1, 1 is 1 over r, and gamma 2, 1, 2 is 0. And then lastly, do partial z theta, partial theta. So I'm differentiating z theta with respect to theta, and you'll get negative r cosine theta I plus minus r sine theta j. Which looks a lot like negative r times e sub r, or z sub r, plus 0 z sub theta. And those are our last two Christoffel symbols. Gamma 2, 2, 1 up is negative r, and gamma 2, 2, 2 up is 0. And that is our set of 8 Christoffel symbols. So we actually have 5 that are 0 and then 3 that are non-zero. So let's kind of highlight what we got here. So gamma 111 was equal to gamma 112 equal to gamma 121 equal to gamma 212 equal to gamma 222 equals 0. And then gamma 1, 2, 2 up was 1 over r. And that was also gamma 2, 1, 1 up. I feel like I made a blunder in this derivative here. Let me recalculate this because the symmetry property is not showing up. So let me recalculate this. I don't think this is right. I'll recalculate this. So partial z theta partial r would be negative sine theta I plus cosine theta j. And that's 1 over r z theta, which is 0 zr plus 1 over r z theta. There we go. So that gives me gamma 211 equals 0, and here gamma 212 equals 1 over r. There we go. That's the relationship I needed. Okay, so which ones are 0? 111, 1, 1111, 1 or 111, 112, 121, 211, and 222. Now gamma 1, 2 down, 2 up equals 1 over r equals gamma 2, 1 down, 2 up, and then gamma 2, 2 down, 1 up is negative r. So that is our set of Christoffel symbols. So in summary, the Christoffel symbols capture how the basis vectors change throughout the space. So Christoffel symbols. Capture how basis vectors change throughout the space. It's the components of the rates of change of the basis vectors. That's exactly what the Christoffel symbols are. Let's see, I call it the Christoffel symbols of the first kind. So note, if I want to get gamma I, j, k down, all I would need to do is lower the index. So I could do gamma I, j, l up times g, l, k down. And we call those Christoffel symbols of the first kind. Questions? And there's a theorem. That says gamma I, j, k down can be written as 1/2 times partial x I of g, j, k plus partial xj of gki minus partial xk of gij. So you can actually write the Christoffel symbols in terms of the metric. But I'm not gonna make you do that. That's nasty. Well, I say that, maybe. But yeah, pretty nasty. Okay, so that is our set of Christoffel symbols. What we could do, so instead, so let me just say note. Instead of expanding partial zi, partial xj in terms of the covariant basis, we could have expanded in terms of the contravariant basis. And we get a different set of symbols. I'm not going to give them a name, but we could expand the contravariant. We could have expanded the terms of partial zi up, partial xj in terms of the contravariant basis. to get partial zi up, partial xj equal to, call it capital phi, I up, j down, k down, in terms of the contravariant basis zk. And this is just some different set of symbols. I'm not going to give them a name, but we'll call it a different set of symbols. So another set of symbols. And we'll use them frequently, but just know what they are. Don't know that you need to know a name for them. Okay. Another thing I want to note is that zi up dotted with zj down equals delta ij. And why is that? So why is that true? Well, zi up dotted with zj down will be equal to, well, I could say that that is GIR ZR if I lower that index on the ZI dotted with ZJ. Which is equal to GIR times ZR dotted with ZJ, which is GIR GRJ, and that's a matrix times its inverse. I'm going to get delta ij because these are matrix inverses. And I'm basically just doing a matrix multiplication right there. So this is a good result. So then, we can rewrite Christoffel symbols. Well, they were partial zi partial xj equal to gamma I j down, k up, z k down. Well, if we take the dot product on both sides with, we'll call it zk up, so zk up dotted with partial zi partial xj would be equal to gamma k ij zk down dotted with zk up, and now that's just a 1. So I can explicitly write gamma ijk as zk dotted with zij, or zi, partial zi, partial xj. So gamma ij down, k up can be written as zk dotted with partial zi, partial xj. So that's another way we could represent the Christoffel symbols, not for practical computation, but for derivation purposes later. now we can say similarly, the phi symbols, phi I up, jk down, can be written as partial zi up, partial xj dotted with zk down is a way we can write the other set of symbols, phi I up, jk down. So we just have a new representation of the symbols that we're going to use when we do other stuff. So, question. This may be the last thing we covered for today. It's a question. How are gamma, so the Christoffel symbols, how are the Christoffel symbols related to, so how are gamma and capital phi related? Is there any type of relationship between them? Well, there is. So the answer, so we start off with gamma, ij down, k up, and we know we can write that as zk dotted with, or zk up dotted with partial zi, partial xj. And now I can say that that is a product rule, partial xj of zk up dotted with zi down. And I say, oh no, you're missing a term, you're right. I have to subtract that away. So partial zk up, partial xj dotted with zi down. So basically took the product rule and subtracted that term on the right. And now this thing right here is delta k up, I down. So this will be equal to partial xj of delta k I minus partial zk partial xj zi down. Okay. Well, delta ki is either 1 or 0, which means the derivative is going to be 0, because those are all constants, either 1s or 0s, minus, and now that is phi k j I. So that's what gamma ijk is. So gamma ij k up is capital phi ji down, k up, negative. So basically, the j and the I switch places, and you throw a negative sign in there. So instead of writing partial zi up, partial xj as phi I up, jk down, zk up, you can write it as negative gamma jk down, I up, zk up. Instead of using those other symbols, capital Phi, you can actually write everything in terms of Christoffel symbols. And one last theorem to end off the day is that the Christoffel symbols have a symmetry in the lower indices. So gamma ij down, k up is equal to gamma ji down, k up. And we can see that from our polar coordinates as like a example. So that is our discussion about Christoffel symbols. Any questions about that? Okay, so like I said, Friday we will not have class, have the capstone presentation, so we'll pick back up with the covariant derivative of a tensor on Monday, and we'll finish that up on Wednesday. Friday we'll have a quiz for chapter 6, and Monday we'll have the final exam, chapters 4, 5, and 6. Going to have a worksheet for chapter 6. Absolutely. I'll post a worksheet probably Monday for chapter 6. So I'll probably go over that on Wednesday. Quiz on Friday. Exam Monday the 18th. Exactly. So our quiz for chapter 5, we need to hash that out actually. I'm thinking maybe Friday morning or Friday afternoon, either like 9:30 or maybe 5 p.m. or something, maybe after all the capstone stuff is done. Just need you guys to let me know in the chat, Discord chat, not necessarily here. So yeah. We'll get back to Christoffel symbols. We actually use the Christoffel symbols coming up, but yeah. Covariant derivative is coming. Any questions? Other questions? Okie dokie. Well, I know today was pretty heavy. Take some time, maybe rewatch it, slow it down, ask questions. But yeah, I think we're getting somewhere. It's some good stuff. It's pretty heavy, so it's the last thing that we're going to cover though. So covariant derivative coming up. Cool. If you don't have any questions, I'll see you guys on Friday in probably one of the capstone presentations somewhere. So, but yeah, we'll definitely have our quiz shooting for Friday morning or Friday afternoon. I'll chat with you guys on the Discord. See you guys later. Have a good afternoon.